Welcome to the Global Composite Experts webinar series. My name is Wenbin Yu. I'm the Director of the Composite Design and Manufacturing Hub. I'm delighted to have all you join us today. This webinar series examines the history and the present capabilities and the future of composites. Our goal is to share the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. Our center is located in the Indiana Manufacturing Institute. We welcome all of you to visit us and explore the cutting-edge facilities and the resources available at our center. At the CDM Hub, our mission is to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. Our ultimate vision is for CDM Hub to become the premier resource for composite design and manufacturing. To achieve this mission, we have developed a powerful website called cdmhub.org, which serves as a platform for the composite community to collaborate and innovate together. We invite you to join CDM Hub and take advantage of the wealth of knowledge and resources available on our website. This webinar series is just one of the initiatives that CDM Hub has launched to serve our community. This webinar series is made possible by the generous support of our sponsors, including Dassault Systems, SciTech Solvay, and Anna Swift. We extend our heartfelt gratitude to our sponsors and acknowledge their commitment to advancing the field of composites. We also welcome other organizations to join us in supporting the global composite community. Together, we can create a better future for our field. This webinar will be recorded and made available on CDM Hub. We will email you once the recorded video is available online. The presentation will be about 45 minutes and followed by a 10-minute Q&A section. All of you are muted at this moment. We ask you to submit your questions through the Q&A box. To ensure the speaker has adequate time to address your questions may be summarized or rephrased. But rest assured that all questions will be forwarded to the speaker to answer at their discretion. Now I would like to invite Professor Dianren Zhang to introduce our distinguished speaker today.
Welcome everyone. It is my great pleasure to introduce today's webinar speaker, Professor Remko Akkerman. Professor Akkerman received his engineer's degree in mechanical engineering in 1988 on turbo machinery and a PhD on viscoelastic flow simulations at the University of Twente in 1993. He started working as an assistant professor in engineering design in plastics and got involved in fiber reinforced polymers. In 2003, he was appointed as a full professor in production technology, keeping a focus on lightweight materials for structure applications with a clear emphasis on composite materials. The group's research is characterized by an integral approach on design, materials, and processing, combining experimental and analytical and simulation work. Professor Akkerman has been the secretary of the European Scientific Association of Material Forming from 2007 to 2013, and since 2009, he is the scientific director for the Thermoplastic Composite Research Center, founded by Tankate, Volker, Boyen, and the University of Twente. In 10 years' time, The center has grown to more than 20 members, covering the whole thermoplastic composites value chain, and to a globally respected institute on thermoplastic composites. He is a member of the scientific committee of flow process in composite materials and of textile composites. Professor Akkerman is a member of the management team of the Dutch Research Center for the High-Tech Materials of the Foto Federation. He further participates in the international advisory boards of large research programs in the UK and in Japan. Now I will give it to Professor Akkerman.
Thank you very much for this kind introduction. It's an honor for me to be able to share some experience and some history, some findings, some ideas acquired over the years on composites forming simulations. I appreciate you all to have joined, whether it's in the morning, in the afternoon, such as here, it's 5 o'clock locally, or at night, or even later. I'll try to have an entertaining story for you, and I'll try to finish nicely on time. And otherwise, I'm pretty sure that our chairman will correct me wherever necessary. Okay, let's have a look. Composites forming. What's composites forming? Well, forming, it's bringing some stuff to a shape where it's more, it's of more use, I would say. Zooming in a bit, we would say, well, composites forming, we interpret that as hot press forming, or as thermoplastic stamp forming, or stamping, or thermal forming. Anyway, this is more or less the framework. I'll discuss this composites forming in the coming 3/4 of an hour, where a pre-consolidated laminate is typically heated in an infrared oven, something like this, brought between two tools which are closed. The composite solidifies, is consolidated, and can be ejected to a final product, possibly after further trimming, and probably to be assembled in a larger structure. So, looking at this process, what does it look like in practice? Well, here you go. Press forming. Here's a laminate. Closing molds. We don't see anything. And that's it, more or less. Just one repetition? Why not? Formed, closed, we don't know what's happening. And then we hope the product that evolves from that is good for our application. Now, things can happen in the meantime, right? So in the time we don't see anything, so with the tools closed, there can be formation of waviness at a very fine level, let's say millimeter size or sub-millimeter, or bigger but still small wrinkles with a bit of deconsolidation here and there. And over a fairly large spatial scale, defects like these can arise up to large folds, which are over longer lengths of centimeters, and easily detected by the human eye. Things you don't want to have in your product, and things you'd rather prevent when designing a product and when developing the tools to manufacture these products. Now, in between the two mold halves, we can't see anything. So even for that, simulations are already very convenient, because, well, there we can easily see what's happening when the tool is pressed. We can see some things happening during the process. And of course, when the tools are completely closed, well, we can no longer distinguish any defects which have arisen? Well, of course, that is very much part dependent. So here's let's say a fruit basket, a composite fruit basket. You always wanted to have one like these, but here you can obviously see quite severe wrinkles in the flanges of this shape, and in forming software, you have the ability to change easily the size of the blank, the shape of the blank, the laminate supports, etc. And you have the relative ease of changing the geometry of your tooling to get a product without these nasty defects, which would which permits actually using the products you've manufactured with all your efforts. So today's lecture is a bit on the background of this kind of virtual forming, where there's a forming simulation requiring, of course, all sorts of input data, giving output data, obviously, which need to be interpreted. And with that, hopefully, the designer can come up with ideas for improvements. So today's lecture will be on the first three items in this list: the modeling with extreme anisotropy, the input data, so the material characterization and what to do with that, and what to do with the results, the interpretation of the results, and what to do with that. Well, let's start with the basics of forming and deformation mechanisms. It's already long recognized that it's easier to decompose the complexity of composite laminate deformations into elementary deformation mechanisms. And originally, folks worried about this biaxial effect under tension, where loading in one direction affects the deformation and the stiffness in the other direction. But rapidly, the focus was more on intra-ply shear of, well, let's say, fabrics in this example, into the sliding of plies to each other, the sliding of the whole laminate against the tooling, and the bending of plies and laminates. Whereas the latest one, compaction and consolidation, is obviously important for the final quality of your laminate, preferably without dry spots, without voids, and all these sorts of defects. If we look a bit closer to the material we're trying to describe, remember we're talking about primarily thermoplastic matrix composites in molten condition. Well, the matrix is obviously in a viscoelastic state, and if we were to assign a modulus to that, it would be typically in a rubbery region, so low, let's say 1 megapascal order of magnitude. Whereas the fibers are obviously remaining in their elastic state, high modulus, let's say order of magnitude 100 gigapascals. So combining that in a prepreg or a laminate, then obviously this laminate has a high modulus in fiber direction and a pretty low modulus for any loading in any transverse direction. So that gives rise to, I would call that extreme anisotropy, 5 decades of difference in moduli. And in these kind of material, large rotations and deformations are possible, except in the fiber direction. We would expect, well, let's say negligible fiber extension during forming. If we would get significant deformations in the fiber direction, then I would guess something is going wrong. So let's say a woven fabric can get significant shear deformation, while the edges in the fiber direction remain of constant length. And for UD materials, obviously that can also shear more or less significantly, and it can also extend a bit in transverse direction, although to a very limited scale in practice. Okay, how to describe this? Well, let's go to simple continuum mechanics, right? So consider this little triangle with an undeformed woven fabric, fiber orientations A0 and B0, and subjected to some sort of deformation described by a deformation gradient F or a rate of deformation D, and that leads to a deformed triangle over here with other fiber directions, and these are nicely mapped by means of the deformation gradient. That's all pretty standard. From that, we would like to define a strain. Okay, strain is also pretty straightforward, right? So that's just the length increase divided over the original length, where you can still argue about, well, which length is then my reference? Is that the original length? So I'd have a total Lagrange approach. Would I use the final length, an updated Lagrangian approach? Anyway, it doesn't, for the fiber direction, this doesn't make a big difference, at least one-dimensionally. Okay, and obviously differential calculus tells something like partial u over partial x is equal to my strain in the x direction. Okay, 2 dimensions, okay, we get a few indices, not very spectacular, all of that. This is pretty standard, I would say. So this works nicely for linear elasticity, but the question is, does that also work for composites forming? Well, let's have a look. Let's have a look. Well, for instance, in this trellis shear, we've got significant rotation of the fibers, right? So we've got an element, the uppercase x, which deforms to the lowercase x, and hence, if we use the uppercase x as our frame of reference, then obviously we've got displacement in the uppercase x direction and also in the y direction. And hence, with a strain, this is non-zero. So this is not a good point of reference. Okay, we'll take the final the final state. Again, we can see displacements or a displacement increment or an infinitesimal strain. Well, this is finite strain actually in the final configuration. So again, we've got, with this rigid rotation, we predict a non-zero strain in, well, this, let's call this the fiber direction, which is obviously wrong. If we translate this to a stress, then this rigid rotation generates huge stresses because of the large modulus in the fiber direction. So that's not what we want. And only if we take the intermediate frame of reference halfway, then we can make the displacement in the x direction equal to 0. But then we need the intermediate configuration. Okay, this is nice, and this is well known in large deformation finite elements, Hughes-Wingett algorithm. So that's pretty standard by now. Often we get a non-zero axial strain except for the average configuration. So so you should use the average configuration to evaluate your strains and your stresses. Okay, nice. However, if we think about the stresses, suppose this element has an initial stress already, then in the deformed situation, this stress should act in this particular direction, in the small x, lowercase x direction. So the stress should be in the final configuration, certainly considering the high anisotropy. So, okay, we need to evaluate the strain in the average configuration and the stress in the final configuration. And that's just inconsistent as far as I can see. So what's the effect of that? The effect of that is if you would do a simple tensile test simulation, fibers in one direction with a modulus ratio of 10 to the power 5 over here, then this is what comes out in a classically okay nonlinear calculation. And this is then the converged answer. Okay, so we thought this didn't make a lot of sense, and that's why we went into ways to accommodate these things and to figure out what was actually happening. So, well, I'm not in the position to give any commandments, but I would definitely advise to use an exact strain definition when describing large deformations during composites forming with this kind of anisotropy ratios. Okay, so large deformation theory. What did it look like? It's always with these potatoes, right? So one potato deforming to another potato. In our case, we've got fiber directions. Well, let's just take one for the sake of convenience here. So A naught is deformed to A or transformed to A by means of the deformation gradient like this. And usually one would use a polar decomposition with a right stretch tensor U or a left stretch tensor R, and these two are both symmetric, and this R is a nice orthogonal, let's say a rotation tensor, and this nicely maintains an orthogonal basis. So either you first deform with U, and then you rotate it to get your deformed situation, or you first rotate, and then you deform it, V, and you get your deformed shape. Both ways lead to the same result, more or less. And the nasty thing is that this retains an orthogonal basis. And in composites forming, that's usually wrong because we can have significant shear deformation, which makes it non-orthogonal in the end. So, what to do with that? Well, we came up with the following. If I can get the next slide, please. We came up with the following solution. There are multiple solutions possible. Our idea was, well, let's use an alternative multiplicative split. So not U or V or whatever. We'll call it G for the time being. We know that the current fiber direction depends on the initial fiber direction transformed by means of F, the deformation gradient. And what we wish is that the length change, any potential length change, is not part of R. And bringing that together, that means that G, our non-symmetric deformation tensor, times A naught is equal to this length change times A naught. Well, from this, if you go through the continuum mechanics, you can figure out that from the right Cauchy-Green tensor, you can compute nicely the strain in the fiber direction. And once you implement this, you have a formulation which correctly, exactly describes your fiber strain. Yeah, and this is just the standard definition of your right Cauchy green tensor. Okay, so that for strain. Now we need to go from strain to stresses. Okay, and yeah, we're in a using a viscous-like material, right? Apart from the fibers, then. So how was that for viscous materials? Well, this is the classical, most general viscous law, where the Cauchy stress tensor contains a hydrostatic part and can be written as a function of the deformation gradient, or the rate of deformation, and the square of the rate of deformation, where these factors psi are a function of the invariance of the deformation rate. And in this case, we want to go to fluids with directional properties. So functions of these, well, let's say a biaxial material, functions of these fiber orientation vectors. Okay, how did that look? Well, we've got a few constraints here. So inextensibility can be written as these products. Alternatively, you could use the fiber orientation tensors, right? So the dyadic products of the fiber orientations, A and B, and then these are the inextensibility constraints, and these need to be added to the incompressibility constraint, usually written like something like this. So that means that we've got an extra stress in our total Cauchy stress plus 3 terms, something in the one direction, which reflects the incompressibility constraint, and something in the A and in the B direction. These 3 terms are not determined constitutively because there's zero strain in these directions, but these typically follow from the boundary conditions. So in this tau, the extra stress tensor, that's where the actual material behavior is hidden. Okay, and okay, it's a function of these fiber orientations, A and B, and a function of the rate of deformation. Well, if you then go through the classical continuum mechanics engine, more or less, imposing form invariance under rigid rotations, then such a function should be an isotropic function of its arguments. And if you then assume linearity, then you end up with something like this as a general, but I would say the most simple way to describe the extra stress as a function of its arguments, the deformation rate, and the fiber orientation vectors, which can be written as these fiber orientation tensors, adding this dyadic product C over here. So that from this we've got 1, 2, 3, 4, 5 viscosities which need to be characterized. I'd like to have it a bit simpler, but nevertheless, this is a well-accepted formulation introduced by Spencer, published in 2000 already, and this equation can be simplified by applying symmetry considerations. Okay. Still, I thought this is a bit complicated. So I've done a bit of algebra here, and I came up with something which all brings it down to a scalar relation, some sort of equivalent shear force or stress resultant, being the division of the dissipation per unit area over the shear rate. And you can nicely work that out in terms of the, let's say the principal stresses or stress resultants. in the bias directions tau 1, tau 2. And if you then consider that for a plane stress situation, we're talking about composite sheet forming, where plane stress is a reasonable assumption in most cases. Then you just need 3 tensors to span the space of this stress resultant. And the A and B tensor are nicely in the fiber direction. So these are fiber tensions, and only this in the Z direction is representing the actual material behavior. So we just got one scalar here, and we can address, or we can formulate that scalar in terms of the shear angle and this equivalent stress resultant. So we just need to characterize only one scalar extra stress variable. And I think that makes life a bit easier. Let's see how we continue from that. Anyway, just a sideline. There are obviously other numerical aspects in composites forming. There's quite a list of them actually. If you, due to the, well, let's say extreme anisotropy, you cannot just place your fibers in any direction. It's most secure if you align your mesh with the fiber angles. Otherwise, silly things happen. There are few elements which can work with non-aligned elements, but these are really few. Further, the large difference in, well, let's say stiffness or compliance in the different directions leads to, well, actually stiff systems. So to get these things convergent, you definitely need consistent tangent operators. Otherwise, well, it's very hard to achieve convergence. Bending is another thing. If you've got bending in plane, you can imagine that the fibers are still resistant somehow to in-plane bending as well. To describe that, you would need second order theory, where a previous lecture has gone into far more detail. And the out of plane bending is, I would say, rather unconventional. So it's dominated by layer-wise transverse shear. If you look at these L shapes and you would inspect the edges here, you can see considerable transverse shear and also slippage between the ply. So this is quite different from what an ordinary Kirchhoff or also a Mindlin element would do. So also that requires a bit of attention, to say the least. Okay. Let's go to the input of this simulation box. Well, of course, to get a simulation running, you need material properties and you need boundary conditions. And the boundary conditions for the composite forming are well, non-standard. Well, gravity. That's easily incorporated, of course, but typically a laminate could be carried by foils, it could be carried by blank holders or grippers, tensioners, all that sort of stuff. Well, luckily, these sorts of things are available in specific software. What I would like to go into is the material properties into a bit more detail. And as mentioned, we had these. Remember, we had these deformation mechanisms, and the first one was in-plane shear. And in-plane shear can be measured in various ways. The standard ways would be typically in a picture frame, something like this, or by bias extension, so extending a plus minus 45 degrees fabric or fabric ply or laminate in the bias direction and inducing shear, which is inhomogeneous over the different areas, the different regions in a specimen like that. That's not so much a problem in the picture frame experiment, but the picture frame experiment is very sensitive to misalignment. And if you have a bit of fiber tensioning in this experiment, well, you're measuring the fiber stiffness more than the actual shear behavior you were looking for. Anyways, that's been researched extensively. We had a very nice benchmark years ago, and gradually, I think we're getting to a stage where we sort of understand what's happening in these kind of experiments, and we've got a reasonable idea how to translate measured force displacement data to actual shear stress or stress resultant versus shear angle data. The response is typically something like this. So the force versus the shear angle, or the force resultant. Typically, the force or the resistance to shear increases with shear angle. This is on a woven fabric, reinforced PPS, and if we increase the rate, then the resistance against shearing also increases. So when describing this material behavior, you need some viscous-like element in your constitutive model, plus obviously a nonlinear elastic element, something like that. You can formulate it in many different ways. For unidirectionals, we had a little success with a picture frame and with bias extension. So we came up with a torsion bar. So this is a pretty thick UD bar, which we were able to mount into the rheometer. So then you have a nice controlled environment and doing standard geometry with large or small oscillations. You can measure the torque against the amount of torsion, and you can translate that to representative constitutive models. But that's also sort of under control, I would say. Then we go to the next mechanism, friction, sliding of plies against tools or whatever. Well, you can do that in different ways. You can go for a pull-through experiment where you pull a laminate or a ply between two rigid tools. Then you may have some entrance effects, or you may pull it out, something like this. But then obviously the pressure is varying during your and non-uniform during your test. So that makes it a bit awkward to interpret. Also here, benchmarks have been performed. Currently, there's also one ongoing. So let's see how we progress there. Quite a few different setups, and I do have the feeling that there's room for improvement. Of course, we believe what we are measuring, but the others are measuring other things. So let's see how we progress. Part of the game. This is our setup, which we just mount in a regular tension tester, I would say, and a typical response. Let's translate the pulling force to a coefficient of friction and plot it against the displacement of a ply. Then if we do the test very slowly, we reach quickly a sort of steady state friction. Here we have a bit of overshoot, and the faster we go, the more overshoot we observe. So this is something, again, to take into account in the friction model you would use in your forming simulation. It does by the way, also depend on the fiber orientation. So if we use a Streetback curve, so plotting the coefficient of friction against the Hershey number, in one orientation we get more or less this behavior. It nicely works with this Streetback plot, by the way, for the fabrics. If we change the orientation of the fibers, so get a more transverse sliding, then we do see some effect on the coefficient of friction. Mind, these are logarithmic scales, so in absolute numbers, the differences are quite more significant. Bending, the third mechanism I would like to discuss briefly with you. Well, this is the classical Kirchhoff bending, normal cross sections remaining normal to the center line. Obviously, these composite laminates are subject to transverse shear during bending as well, and obviously there may also be slip between the plies. So, what to do with this? Again, well, this is the what happens in a unidirectional material. Again, the same L shapes as shown before. So significant transverse shear and repeating this interply slippage for 090 L-shaped specimens. So what to do with that? You can go for a static cantilever test introduced in 1930 already. It's less than 100 years ago, but still of considerable age. So seeing how a laminate deforms under its own weight and the gravity. Of course, doing that on thermoplastic laminates, you need to heat this box to forming temperatures. We thought it would be convenient to do something that is sensitive or that can measure the sensitiveness, the sensitivity to rate as well, to be able to control the deformation rate. So we came up with this Kawabata type inspired setup, again in the rheometer, so we can use the rotation of the rheometer to bend this specimen over here, which can be a laminate or a single ply, and we can measure the torque and plot that against, well, let's say the rotation, or translate it to the curvature of this specimen. And this is a typical response you would get. So the bending moment increases with curvature, an elastic effect, and if we increase the rate, then obviously the stiffness, or the apparent stiffness, also increases. To understand what we're measuring, we did this sort of mesomechanical analogon with elastic fibers separated by a viscous matrix. And if you go through the equations, then you end up with this diffusion equation of the rotation angle. And well, that then apparently should describe the bending behavior of a structure like this. Well, okay, let's see how that works. If we use this kind of model and evaluate it by means of the bending moment versus the rotation angle, we get these black curves, which reasonably represent what we're measuring, apart from an increase in apparent stiffness at the higher rates. That's not included in this particular model. So again, there's room for improvement. And of course, this being very different from the classical elastic bending, this will also require a specific shell formulation to account for this. Well, then the question is, okay, we're measuring things. How many parameters do we need to describe a material? And well, the classical note from John van Neumann is, well, 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. Let's see, if we use 4 parameters for this bending behavior, we've looked into our full database. A rather significant portion of our database, we could fit the behavior of 10 very different materials with 4 parameters, describing the temperature behavior, describing the deformation behavior, describing the effect of the slope. Okay, so this is the slope, this is the rate, this is the temperature, and then there's one further parameter, a proportionality factor. Well, it's like an E modulus for elastic systems, which characterizes the materials. Well, we think we get a decent fit for all these 10 materials. So to our idea, this would be a reasonable description of the actual bending behavior. Of course, we can always improve on things. If we go for 5 parameters, and we can also fit this tail over here, so the startup function. But nevertheless, we do think that it's good to consider also for user friendliness to go for a minimum amount of parameters to describe the actual underlying material behavior, rather than overfitting with far many more parameters of what we've recorded in testing one single material. Okay, concluding on all this modeling stuff, here we've got an example already of a few years ago, 10 years ago, I see, where we compared DIC data. So a grid was plotted on a formed laminate. It was before forming, was formed, and from that we could get the strain distribution, the shear strain in this case, and compared to the simulated results, we were reasonably pleased, I must say. So the green areas, small shear strains, these are predicted in the wrinkle-free areas. We can recognize some diagonal bluish patterns over here, which we also recognize in the experiment, where we predict waviness. We also saw local wrinkling in practice, and the global wrinkling is just correctly predicted. These falls are just spot on, provided you have the input of the accurate material characterization data and you have an accurate representation of the boundary conditions. It sounds trivial, but it's easily overlooked. So pretty happy with this. Okay, so last part, what to do with all this data. And well, we set out to predict manufacturing defects. So what are defects then? Okay, these could be ply splitting, transverse cracks, matrix degradation. Okay, that sounds like temperature, oxidation, and that sort of situations, voids, dry spots, delaminations. Probably connected to consolidation pressure. Surface defects, okay, could be due to severe traction, so sliding stresses, contamination. Okay, that's more a workshop thing. Fiber distortions and fiber breakage. And if we just look at what the simulations bring us, then transverse stresses will relate to this defect. Voids, dry spots, and delaminations will relate to the normal stresses during our forming simulation. Fractions, well, we can have a look at the shear stresses in our contact elements. The fiber tensions will have an effect on resin squeeze out and fiber breakage. And that sort of practically only leaves us with these fiber distortions, folds, wrinkles, and waviness. The thing I started with, if you remember from my second slide, I think, something like that. Okay. The nice thing about these simulations is that we can see what the laminate is doing during the deformation, during the forming process. And at incomplete tool closure, we can have a look at whether whether waviness or buckling regions arise. So in the actual laminate, you'll have the gray line over here, and if the elements are large enough, then the elements will simply follow the large buckles. And the smaller these wrinkles become, the harder it becomes to represent these with the elements. So this one is definitely sub-element level. It's very hard to represent in the actual simulation. But still, something may happen if there's a bit of compressive stress in the laminate direction. And then if we go from an open tool to a closed tool, then the large defects will simply lead to faults at complete tool closure. And the medium ones, well, they can be pressed between the two tool halves, and they can sort of rotate to waviness in plane. Whereas the small ones, well, they can be compressed and leading to compressive stresses in without any in-plane waviness. So let's have a look what that looks like. So here we've got these very small defects, some in-plane waviness, medium defects, and some large folds. Well, we've already seen that these large wrinkles give rise to a highly distorted mesh. These are easily seen in your simulation. The medium ones, indeed, if we look at areas like this, what we observe, if we look at the shear angle or the shear, the accompanying shear stresses, we nicely see this alternating in-plane shear at regions where these kind of defects are occurring. So also these can be detected just by looking at the simulation data. And these ones are typically related to, well, the blue colors, negative stresses over here in the different plies. So here we get compressive stresses, and these nicely relate to these micro buckled regions. So also here, the simulation provides information to predict these kind of defects. So various stress components can serve as indicators of various defects. And it's also very useful to look at what happens during the process, is that buckled regions will be a starting point for the final folds and wrinkles in the final product. So not everything needs to be simulated explicitly, and not only the final stage methods. However, better defect indicators would definitely help the software user. Okay, so concluding this one, what's next? Well, in the end, virtual forming is only part of the puzzle. I would, of course, say, well, the forming determines the structure of your part. So if you can't predict your structure correctly, then you'll have a hard time in predicting the performance of your structure. But nevertheless, let's be fair, virtual forming is only part of the puzzle. And first of all, this part can be improved. So yes, we're looking for more accurate constitutive models. Yes, we're looking for more accurate finite element formulations and more accurate defect indicators. And all this requires ongoing benchmarking, both on the experimental side and on the modeling side. Then, of course, being part of the puzzle, this kind of software needs to be integrated in design systems. Digital twins are all over the place, incorporating more and more information. Well, there's a whole list of those. Sorry for the amount of text, but you can imagine that it's part of a bigger thing. And subsequently, it only makes sense if the tools can be used if the tools are accessible. So you should get your software out of the academic environment into commercial applications, including documentation, training, maintenance, updates, including also the material characterization and an accessible database, all that sort of stuff. And finally, we can only get this to work if we are able to train professionals in using these kind of tools and to motivate future engineers. And all this together, well, gives you a sort of balance, On one hand, we'd like to have more accuracy, but probably that goes with more complexity of the software tools. And on the other hand, we want to have more applicability, where user friendliness is an obvious thing to strive for. So there I come to an end, and I would like to thank lots of people. First of all, the bright students, former students, having performed all the work presented here. I've done nothing as usual. To our industrial partners, governmental agencies for their continued support of this work. Definitely to the TPRC for road mapping and long-term commitment. And finally, to today's audience for your kind attention. And I'll be more than happy to answer any questions you might have. Thank you.
Mr. Akkerman, thank you very much. And we'll look for some questions here from the audience. We have a few minutes. And we've talked a lot about the different characterization. Someone raised a question right off the bat. How much does the matrix properties influence wrinkling in your experience?
It's a combination of the matrix behavior. So low viscosity versus high viscosity definitely makes a difference. Further on, it's also the reinforcement structure, which is pretty important, I would say. So even comparing one carbon peak material to another carbon peak material with different pre-pregging processes and different structures, that makes a difference. I hope that answers the question.
Thank you. Thank you. One more detailed question that popped up here was, given the potentially large slippage between plies, how can interlaminar contact between plies be treated efficiently using an implicit solver?
It's a question of as much as possible using consistent tangent operators to properly describe that. We don't take into account deconsolidation regularly, so the plies remain in contact in general. That solves quite a bit of the problems, I would say. So effectively there's quite some adhesion anyhow. So I think that is still pretty realistic and pretty defendable. And with that, implicit codes work excellently, I would say. No problem.
Thank you. I think we have time for one more question here. And you've addressed this to some extent, but quite a bit actually. But what are the main limitations of current constitutive models for composite forming simulation? I know you've kind of touched on that as you've gone into your future work, but if you maybe summarize that for this.
Yeah, I'll be more than happy. I think the biggest one, the biggest fish at the moment is in bending description, and in plane shear, I would say the current descriptions work decently. There are quite a few different constitutive equations. So in terms of applicability, it's a bit of a nasty one. In terms of friction, also there is room for improvement. I think most of us are working with a steady state friction, whereas there's still quite something happening before reaching that steady state. So also there's room for improvement, trying to get a dynamic friction law rather than a steady state friction law.
Thank you for that. And again, thank you for the entire presentation. Thank you to the audience.
Thank you.
A reminder to the audience, this has been recorded. You can be able to access it in the future on cdmhub.org. And this lecture today concludes our 2022-2023 Global Web Composites webinar series. We'll start this again in the fall, and look for emails from us as we get this going. And once again, a hearty thanks to Professor Akkerman and the opportunity to listen and interact today. Thank you.
Thank you so much. Okay. Bye-bye.